Okay, so basically we kind of numerically proved the Euler's formula, right? By basically increasing n and c, the result gets closer to 0, right? And basically what's left is really to prove that as n increases indefinitely, the error would drop indefinitely. That'll be a formal proof of Euler's formula, right? That will leave to mathematicians. So here we are, let's say we stick with that. So now the question becomes, okay, so this is an experimentally observed behavior, right? Is there a way to figure out ahead of time, okay, how would the error of the forward Euler decrease as I increase my n, right? Is this behavior only true when I'm integrating this particular equation, right, trying to prove Euler's formula? Or if we apply the same Euler's formula to a different equation, an equation where I don't have an analytical solution, should I also expect the solution error to drop linearly, right? Or let me say, to drop to n to the minus 1, just to be precise, right? Would I expect, okay, if I want the error to drop by a factor of 10, should I just increase n by a factor of 10, or should I do something different? So here comes the power of mathematical analysis. So the question is, how do we analyze the accuracy of such time discretization? The analysis is really what happens as n goes to infinity, right? What happens if we already have a very big n and we further increase it? So when n goes to infinity, what happens to my delta t? My delta t goes to 0. So the formal mathematical analysis of the time discretization is what happens to the error of the approximation, right? We are approximating the time derivative. What happens to the error when my delta t goes to 0? How do we perform that analysis, right? So what we are doing is we are approximating du over dt. We are approximating that by u at t plus delta t minus u at t divided by delta t. So the question is, what happens to this approximation error, right? My approximation error, which is a function of delta t, is equal to the difference between what I'm trying to approximate and the approximation I'm using. So it is du dt, the left-hand side, minus the right-hand side. Okay. Does anybody have any idea of how do we proceed? How do we figure out the behavior of this guy as t goes to 0?
So as delta t goes to 0, that should converge to 0 because the term on the right will approach the actual definition of the derivative.
Yeah, the right-hand side is going to approach the actual definition of the derivative, but how fast does it approach? Here's the question, right? I mean, the accuracy of the scheme or how desirable a scheme is very different. If, let's say, as I increase my n by a factor of 100, I'm only decreasing my error by a factor of 2, right? That's going to be a very, I should say, bad scheme, right? Because if I want a more accurate solution, I need to spend a lot of extra computing time. Okay, versus another scheme, if I increase n by a factor of 2, I decrease the error by a factor of 100. That would be a much better scheme to use, right? So how do we figure out which case it is?